Hi, Math 30s. This is the newest unit, so that if you look on D2L, you need to make sure you've printed off the booklet. It's called Counting Methods, so make sure you have that printed off. Um, we'll get through this, and I think we'll get through one more unit we'll potentially have time for. So, yeah, let's get started. So on the first page of the booklet, if you ignore the timeline that's half empty or totally empty in there, at the top it says explore. So again, make sure you have the booklet ready to go. I'm kind of skipping out on stuff because all I have in my smart file is my key to this. So it says a student is ordering pizza for the class. How generous. There is a special for two topping pizzas where a choice of one meat and one vegetable is required. The meat selections are pepperoni, salami, or ham. The vegetable selections are mushrooms, green peppers, tomatoes, or olives. Create a sample space to list all possible two-topping pizzas if you must choose one meat and one vegetable topping. So I actually want you to try that out quickly. See how many different pizzas you can create that have two toppings, one from the meat portion and one from the vegetable portion. So see what you can do. Pause the video here quick and see what you can come up with for the possible options for the pizza or how many outcomes there are in this situation. So pause it because I'm going to click on to my answers here. So what I did, well, let's put my pen on. Um, what I did is I created kind of a table. So I could have listed pepperoni with mushroom, pepperoni with green pepper, pepperoni with tomatoes, pepperoni with olives, and then salami with each of them, and then ham with each of them. But I made just like a little chart is one way of organizing it. You probably did it the first way that I was kind of saying there, and that's fine. So I made down my side here, I made pepperoni, salami, and ham. And across the top, I had the vegetables, so mushrooms, green peppers, tomatoes, or olives. And so what we can see is this little check mark here. I guess I should use this. This check mark here represents a pizza that has pepperonis with mushrooms. This one is a pizza that has salamis with mushrooms. This one here is a ham with olives. So what you could do is you could then count up how many different outcomes there are within the situation. So there's 12 possible outcomes in this situation. It says explain how you can determine the number of possible pizzas when choosing one from each of three choices for meat, four choices for vegetable, and two choices of crust without creating a sample space. So this is what we already had, right? We had three choices for meat, four choices for a vegetable, but now we're adding in two different types of crust. So a regular crust and a thin crust or something like that. So we know in total for that first part that three choices for meat and that four choices for vegetable came up with 12 outcomes. So what we could do from there is we could then multiply that number by 2 because there are two different crust choices. So this one would be a salami with tomato. We could either have that with the regular crust or with the thin crust. So there's two different options. So again, where that one comes from is 3 choices for meat, 4 choices for a vegetable, and 2 choices for crust. Got us to 24. So the next part, is exactly what we were talking about there. So the total number of possible outcomes can be determined by multiplying together the number of outcomes in each category. So this is called the fundamental counting principle. And this is going to apply throughout the unit. So there'll be places where you can apply this principle and there's places where it won't necessarily be particularly useful, but this is something that we'll see throughout the unit. So kind of our general form of, or our general information of the fundamental counting principle is if there are A representing any number of ways to complete a first task, and B ways to complete a second task, or again, we're saying tasks here, but your task is choose a meat for your pizza and choose a vegetable for your pizza. And no outcome from the first affects the second. So that's important. It's not saying there are 3 choices for meat on the pizza and 4 choices of bread for a sandwich where if you picked a pizza, you don't have to worry about the sandwich situation or something, but that's important and we'll see why a little bit more later. But no outcome from the first affects the second. Then there are A multiplied by B ways to complete the tasks as a pair or together. So for example, from above, if there were the 3 meat choices, the 4 vegetable choices, and the 2 crust choices, what we could just do is multiply. In this case, it's A times B times C. And we could keep going with it, right? If we had different choices for boxes and different choices for a drink it comes with or something like that, we would just keep multiplying and so on and so on and so on. But you're always multiplying in this case. So the next part, it says determining the number of outcomes with no restrictions. We'll start talking about restrictions today. So example 1 here, oh sorry, Marcy is looking to purchase a new stereo system. She can choose from 3 different CD players, 5 different sets of speakers, and 4 different stands. So she wants her system to include a CD player, a speaker set, and a stand. And we know that there's different options within each of those categories. So use the fundamental counting principle to determine the total number of possible stereo systems that she could choose from. So I do this all the time for these questions. This is just kind of how you set it up, is I always make these little blanks. And usually I will define it underneath, and we'll see why that gets important. It seems pretty easy for the first couple questions that you think that this isn't important, but I always end up for FCP questions, I always write out what I'm looking for. So we have CD players, we have speaker sets, and we have stands. So it says since there are no restrictions, so there's no restriction that if you buy CD player 1, there's a set of speakers that doesn't work with it or something like that. There's no restrictions. It doesn't say anything like that. So there are 3 possible CD players, there are 5 possible speaker sets, and there are 4 possible stands. So what you would just be doing is 3 times 5 times 4, which gets us 60 different possible stereo systems that she can have. So the next question, did I add that on? It says, if Marcy has the choice of buying a stand or not, so maybe she doesn't necessarily want a stand for her stereo system, we can kind of think about what that means. So we can think of it in 2 ways. So we can look at the number of stand options plus the number of no stand options. So these are 2 ways that we can do it. So we can do it like this, or we can do it as an all-in-one calculation. And I usually end up doing the all-in-one calculation. So this is kind of this first way of looking. Oh, geez, sorry, my tablet's funky. Since we know she has 60 stereo options with a stand, we can find out the number of options without a stand. So again, there were 3 different CD players. There were 5 different sets of speakers. So there are 15 different options without a stand. We could, I'll talk about that here. So therefore, the total number of options with or without a stand is 60 plus 15, which is equal to 75 different ways if she's buying a stand or not buying a stand. So she has kind of that option still. So an all-in-one calculation, so this is a different way to go about it, is 3 different CD players, 5 different speaker sets. So stand versus no stand. We know there are 4 stands, but we can also make the choice of no stand. And that's making a choice, right? So we have the option of having no stand at the end, or no stand in the stereo system that she wants. So we would actually do 3 times 5 times 5, and that comes to 75 different stereo systems. So that's another way that you can consider it. And so this is kind of, we'll talk a little bit more about this later. So in the last unit, we saw the word or as being important. When we have an or question in this, what we're going to actually be doing is adding things together. And we'll see this again later, so don't worry about thinking about that too much right now. But when we see an or question, we're going to be adding stuff if we do it as a two-part question like this. So the next one, oh, still on Marcy, says determine the number of options Marcy would have if there are also two different amplifiers to choose from, and her stereo system consists of, so this is another or question. We see there's a big or there. So we know we're going to be adding these different options. So a CD player. Oh, I don't know that I necessarily need to write this. Sorry, I'm just going to cross it out. A CD player, set of speakers, and a stand. Or a CD player, a set of speakers, a stand, and an amp. So what we want to look at is, so again, CD, speakers, stand, and then our or here, we're going to add the options if she's now having an amplifier as an option. So CD, speakers, stand, and an amp. So there were 3 different CD players, 5 sets of speakers, 4 different stands. So this is the option of if she has no amp, and then this is the option of if she decides to buy an amp. So there were still 3 CD players, 5 speakers, 4 stands, and now it says there are 2 different types of amps that she could purchase. So we know this one is equal to 60. This is equal to 120. So 60 plus 120 is 180 different outcomes that we can have, different possibilities. Or different things that she can choose from. So hopefully that makes sense for you. Ooh, cut off a nice chunk there. Oh, just the title. So it says example 2, determining the number of outcomes with restrictions. So we're going to have a little bit of restrictions on there, and we'll see what restrictions mean. So when there are restrictions given, you need to deal with the restricted spaces first and then fill in the rest. So since many examples include digits and letters, it's important to know how many digits and letters there are. So in this unit, you're going to need to know a couple different things. You need to know that digits are 0 through 9. So there's actually 10 digits. Letters, there are 26 letters. If we talk about a standard die or a standard set of dice, there are 6 sides. Cards, you actually need to have a bit of an understanding of what a deck of cards is. So 52 cards. There are 4 suits. So oh, I kind of drew this line. So there are hearts, diamonds, spades, or clubs, and spades. I can't really draw it, but looking kind of like that. So you should have an idea of what the cards, we'll see a lot of questions with cards, so you actually need that idea. And these 2 suits are red, these 2 suits are black. Just when it starts to come up, I'll go over it again then. So that relates to this. So there are 10 digits, 0 through 9, and 26 letters A through Z. So a bank PIN number, so this is the PIN number on your bank card to take out money or use it, involves 4 digits typically. I know there's a lot of places that have 6 digits, or you can pick how many digits it has. My bank, it's always been 4 from what I've known. So how many PIN numbers are possible if there are no restrictions? So if there's no restrictions, you can have whatever number you want. So we know the first digit can be the numbers 0 through 9. So you could make your password 0000. You could make it 9999. You could make it any sort of thing in between that. So If the first digit, there's no restrictions on it, there are 10 possible digits that it can be. The second digit, same thing. If there are no restrictions, these are all going to be tens because they could be any digit. So that gives us 10,000 possible PIN numbers. So the next one is if no digit can be repeated. This first, second, third, fourth. So again, I said I'll write this in always. I always do these little lines when we're doing a fundamental counting principle question. So if no digit can be repeated. So in the first spot, we still can have any of the 10 digits, 0 through 9. In the second spot, we can't have whatever we picked here. So if we put a 0 here, we can't have a 0 there. If we put a 1 here, we can't have a 1 here. If we put a 2 here, can't have a 2 there. So there's actually 9 digits that can go there because we can't have whatever we had in the first position copied here. The third, so again, we can't have any repeated digits. So whatever I have in the first spot and whatever I have in the second spot can't be in the third spot. So there's 8 possible digits that can be in the third spot, and you're probably seeing the pattern. The fourth can't be the same as the first 3, so there are only 7 digits that can go in those spots. So 10 times 9 times 8 times 7 is 5,040 different PIN numbers that can be generated if we have a restriction. So that's what a restriction is in this case. It's saying you can't do something, so that's a restriction. If your bank's weird and says the PIN number must end in a 3 or a 5. So again, we still have 4 possible places that numbers need to go. So we know that the last digit must be a 3 or a 5. So in total, there's 2 different digits that it can be. It can be a 3 or it can be a 5. There's no other restrictions other than this last digit. So we're just going to say all of the other ones are still tens. So 10 times 10 times 10 times 2 gives us 2,000 possible PIN numbers. So our restriction here is just on that end part that it needs to be a 2 at the end, or sorry, a 3 or a 5 at the end, giving 2 different possible options for what your PIN number can end with. So hopefully that's kind of making sense. We'll do just a couple more before getting to practice. I just need to check that it's recording. Oh geez, is it? Yes, thank you. So a license plate has 3 letters followed by 3 digits. So it now is 3 letters followed by 4 digits. So probably getting closer to 10 years ago that would have changed over. So it used to be 3 by 3, now it's 3 by 4 mostly. How many license plates are possible if there are no restrictions? So we're just going to do it based on the old ones, and then we can talk about why it's now 3 by 4. But so a license plate back in, let's say when I first started driving, unless you had a specialty plate or a vanity plate or something, it had 3 letters at the beginning followed by 3 numbers. So I know that my first one needs to be a letter, my second one needs to be a letter, my third one needs to be a letter, my fourth needs to be a digit, my fifth and my sixth need to be a digit. So there are, if we say there are no restrictions in the license plate, so you could have AAA 111 or 000, or you could have ZZZ 999 or something like that. So in this case, we have no restrictions. So in total, there are 26 letters. So if there are no restrictions and you can have repeats, we have 26 options in the first, 26 options in the second, and 26 options in the third. And as far as digits go, again, no restrictions. There are 10 possible digits. The next one, it says no letter or number can be repeated. So that's similar to the pin question that we had previously. So if we know that still letters in the first three, digits in the second three, we know that there's 26 possible letters that can go in the first place, but once we have put a letter here, we can't have the same in the second spot. And then once we've put a letter here, we can't have the same as that or the first one and the third. Digits, in the fourth position, we can have 10 different digits. And then we can't have a repeat of that digit, so 9 and 8. Sorry, I never actually multiplied this out for you. So 17,576,000. And this one is 11,232,000. So the first letter must be a J. Oh, is our next one. And the first letter must be a J, and it must end in an odd number. So hopefully you're thinking about what that means. So the first letter must be a J. So we know that there needs to be, or there is one possible thing that can be in the first position. It has to be a J. Most of the new license plates that came out shortly after they changed to the 3x4s were Bs at the beginning. And that wasn't a has to be, that's just where they started. They don't start randomly assigning them. They start pretty regimented in how they're assigning them out, so and how they print them. So most of the license plates, if you look around, start with a B. So first letter must be a J. There's no other restrictions though. So there are 26 possible letters that can be in the second position and 26 that can be in the third position. We could have other restrictions that say first letter must be a J. There can be no repeats, that this would be 125 because your second letter couldn't be a J, and then this would be a 24 if there were more restrictions. And it must end in an odd number. So this one doesn't matter. This one doesn't matter. It can be anything. The last one, so odd numbers. So again, thinking what our odd numbers are, it needs to be 1, 3, 5, 7, or 9. So there are 5 different digits that can go in that last position. Yeah, let's just zoom on. We can talk about license plate stuff, or we can just keep going. This one's kind of a tricky one. But at least questions will sometimes come up. So it says, using the example of the 4-digit PIN numbers, determine how many PIN numbers are possible with at least 1 digit repeated. So we know, actually it talks through most of this. So it's sometimes easier to approach these questions similar to like the set theory stuff. So if we were to kind of draw a Venn diagram of this possible situation, so our universal set would be how many different 4-digit pins, and we calculated that out. So that was the 10,000 number. So again, that was 10 times 10 times 10 times 10. So that's with no restrictions. So we know that everything needs to add up to 10,000 there. So we either have PIN numbers that have any number of repetitions or PIN numbers that have no repetitions. So repetitions, we could have 1 repetition, we could have 2, we could have 3, or we could have all 4 numbers the same. We know that that would not overlap with the set of no repetitions, so that's no numbers repeated. This would actually represent everything within this universal sets. Repetitions versus no repetitions. There can't be something out here that has neither repetitions nor no repetitions. So there's nothing outside of the universal or outside of those two sets in our universal set. So we know that repetitions plus no repetitions needs to equal 10,000. Because again, that's our universal set. So in this example, we can take the total number of possible outcomes, universal set, and subtract the number of outcomes that we do not want. So there are 10,000 possible PIN numbers, and we calculated this out on the last page as well. So that with no repetitions. So no repetitions was 10 times 9 times 8 times 7, which was 5,040 different ways. So if there are a total of 10,000 PIN numbers and 5,040 of them have no repeating digits, then the rest must have digits repeating. So at least one repeat, which is what this question is asking. It's not asking how many have two numbers repeated or something like that. It just says at least one number repeating. So if we take that 10,000 from the last page and subtract, so again, this is the no repeats, we get 4,960 PIN numbers that have repeating digits. So this is kind of, let's call it foreshadowing into the next unit. So probability in the fundamental counting principle. So know that if this unit is a bit of slog, it ties into the next unit. So make sure if you're coming across some difficult questions or if you feel a little bit confused, get to me right away so I can help you kind of clarify it. Again, make sure you peek through those CBE online links that I have, or even peeking to Khan Academy if you want to find it out really quick. Sometimes I don't answer my email for a couple hours. So you can look either at the CBE online stuff on D2L or look up Khan Academy questions as we go. So it says a multiple choice quiz has 5 questions. Each has 4 answers from which to choose. Okay, so it's just a little short quiz. There's 4 multiple choice, so A, B, C, D for each of those. So in how many ways can the quiz be answered? So we have question 1, question 2, question 3, question 4, and question 5. So let's say this test is in Mandarin, in which I have no experience and no knowledge of anything within Mandarin. So if it was a test in Mandarin, I would have no idea what I would be doing. So each question, so question 1, there are 4 possible ways to answer it. Question 2, there's 4 possible ways. Question 3, 4 possible ways. 4, there's 4 possible ways. And 5, there are 4 possible ways to answer it. So there are actually 1,024 different ways to answer that test. So we could put in A, or A, C, B, C, A, or something like that. There's so many different ways to answer the test. There's over 1,000 ways to answer that test. So if there is only one way to answer the quiz correctly, what is the probability that I would get 100% on this Mandarin test that I have no idea? So there's only one right way to answer it, and there are 1,024 possibilities to answer it. So the probability of me getting 100% on a test that I have no idea what I'm doing is 0.00098. You could convert that to a percentage, which again, we'll do this in probability. So 0.098 by multiplying by 100%. Percent chance of getting 100% by guessing. So that's only a 5-question test that I have less than 0.1% chance of getting 100% just based on guessing. So we'll talk a lot more about probability when we get to that unit, but that's how those sometimes apply. So you now have practice questions on the next page in a bit. So go through all of that. There are some probability ones. So if you need to peek at my notes for the answers when you hit to some probability ones, please do. And next day we'll do permutations and factorials. All right. See you later.